languages.
This video is subject to copyright only. To maximize the use of this session, please connect a headphone and mic if you can. Stay in a quiet place. Adjust the sound of your computer. Close all other programs running on your computer. The instructor will direct you to open any other required program to use. Close chat programs and social media such as Facebook, Twitters, Messengers, WhatsApp, etc. Maximize your screen to see the four corners on this slide on your screen.
Context-free languages is a superset of regular languages. What we always describe here is how we can define a language. So if we have two different variables a and b, a to the power n, b to the power n, where n is greater than 0, is defined as a language. So you can represent this language as w, a subset of w to the power of r, where w can be lambda or phi, or w can be any other symbols. And w in this case will be the connotation ab. Regular languages, it's a subset of context-free languages. If I want to understand context-free languages, it can be represented by context-free grammars, or on the other hand by push-down automata. In this lecture we will focus more on context-free grammars. However, we covered push-down automata in the previous lectures, so please refer to the previous lectures for more information. Also, you have to understand that push-down automata, as we explained before, it has a stack, and the stack will have automaton, and the automaton will be able to interpret the connotation of the stack, and in this way we can build a language. To focus on context-free grammar, grammars express languages, and a simple grammar inside the English language, which majority of us will understand, is sentence. And the sentence could be a noun phrase and predicate. The noun phrase will be split into article and noun, while predicate usually it's a verb. Article could be a or the. Noun could be cat or dog. In this particular example, we want to focus on a simple subset of nouns to give you the context, and then we can make it more complicated. Verbs can be run or sleep. So in this particular case, we have two articles, two nouns, and two verbs. A derivation of a string, such as the dog walks, will look like noun phrase and predicate. The noun phrase can be split into article and noun, while predicate can be split into verbs. And in this case, I can substitute an article with the or a. I can substitute the noun with dog or cat, and I can substitute the verb with walks or sleeps. A derivation of the string a cat runs is very similar. I will have the noun phrase, I will have the predicate. In this particular case, the predicate is an actual verb, and the verb could be runs. However, the noun phrase can be split into article or noun. If I want to take this grammar and then I want to define a language of a grammar, this will be the set of the language of a grammar, where I can see all articles, all nouns, and all predicates. In this case, I have two articles a and z, two nouns cat and dog, two predicate verbs, which is run and sleep. And this will show all possible combination, which end up to be 2 to the power 3, which basically 8 different combinations. If I want to talk about production, so production or how to build a more complex or a more generic production, in this particular case, I have a noun or a sentence. A noun will lead to a sequence of terminals such as cat. Sentence will lead to a sequence of variables such as noun, phrase, or predicate. And in this case, I can make it recursive, so the noun phrase can be also a sentence and then it can be replicated. Another representation can be a grammar defined as S, where S will be A, S, B, and A and S can lead to lambda, where lambda basically is the empty sentence or the empty grammar, or basically null or zero. So in this particular grammar, I will have it S, where S will be ASB, or A or S lead to lambda, which is the empty predicate. So the derivation of this string will be either AB or ASB or lambda. So in this case, I can drive ASB, and then ASB will drive AASBB, and so on. And if I decide at this particular point that lambda is S is equal to lambda, then it will be AABB. So I can show you here multiple derivations, and if you want to understand how an exam will come, basically you will be given a grammar such this grammar, and then from this grammar it will ask you to have 3 or 4 possible derivations. Here you can see a derivation where ASB, then it will lead to AASBB, then triple AS triple B, and so on. If you don't assume lambda, S to be lambda here, it can keep going on, and then you can have quadruple A, S quadruple B, and then if it's lambda, it will be AABBB. So the grammar is ASB, S tend to lambda. The derivation could be AABB. It's a valid derivation from this grammar. Another derivation. I can describe the language of this grammar as L equals the bracket of A to the power n, B to the power n, where n greater than 0. So this notation can define it as a set. So in the top here, I derive the grammar as a rule. Here I'm deriving it as a set. A convenient notation where we use the star notation, so S will lead to star notation triple AB, is this is a valid derivation. So in this way, I can use this derivation here instead of deriving it in this way. In general, we write W1 will lead to star of Wn, where star means the predicate of, or the cross products of Wn, and this will lead to W1, W2, W3 all the way till n in a 0 or more derivation steps, and trivially W equal to W. So if I want to show you both sides of the equation, here I can give the example of the grammar, and here I can show the derivation of the grammar. Here is in the next slide we will talk about the convenient notation. So this could be another way to do the convenient notation. So S will lead to ASB or lambda, and in this case we can use this language to define article, for example. So an article could be A or an article could be Z. So in this case, article lead to be A or Z. So the formal definition of a grammar can be the set of variable, set of terminal symbols, start variables, set of productions. A context-free grammar will be defined as G equal to VTSP. All production P are in the form of A lead to S, where A is the variable and S is the string of variables and terminal. An example of a context-free grammar, we still use the same example as ASP. So you have S, where ASB will lead to, or lambda, where all the productions will look like S lead to ASB, where S tend to lambda. So in this particular example, where we define the grammar using 4 variables, you have S as a variable, you have T as AB, which is the terminals, and S is the starting variable. And the production describe how we can produce it. Either lambda means I have empty sentence or empty grammar, or I have ASB, where S can be ASB or it can be lambda. So the language of this grammar will be the language of G, where omega is the string of terminal or lambda, and S is the production, which will lead to multiple product of S, as long as W will belong to T star. So the context-free grammar S lead to AS and lambda will be equal to the language G, where AN, BN, where N greater than 0, since there is a derivation that S star A power N P power N for any N greater than 0. So this language-free grammar will be described using L and LG. Here is another example that this language can be AN, N where N greater than 0, is a context-free language, since the context-free grammar in the form of S lead to AS and lambda. So what we are doing here is we are basically setting a multiple example how we can drive the same language or the same grammar. So what we covered till right now is the context-free grammar, and we define the context-free language, and in a nutshell, the context-free grammar will have the symbol OR, where you can have A, S, B, or SS and lambda. And in all of these derivations, we demonstrate a way to drive different language or sentence. In the next module, we will talk about derivations and derivation tree. Derivation order and derivation tree. To understand derivation order, we consider the following example grammar with 5 products. S lead to AB, where A will lead to small a, and capital A, or capital A will lead to lambda, where B will lead to capital B and P, where B will lead to lambda. Now, we have to understand that if we have a recursive relationship like that, we must also have the lambda relationship. Because if you don't have lambda, this recursively will be indefinite predicate or indefinite sentence. If you want to see the example here, and if I want to drive the symbol AAB, what I will say is S lead to AB, and then I will remove the A and substitute A with AAA, and then I will remove the A to be lambda, because rule number 3, A equal to lambda, and then I will end up with the symbol AA and capital B, and then I will substitute capital B with B and small p, and at the end, at step 5, I will apply rule 5, where I will have B equal to lambda, which will lead to AA and P. So the rightmost derivation of the symbol AAB will look like this, and at each step we have these symbols. The leftmost derivations will be like that. So in this case, I have S and S. I can go leftmost or I can go rightmost. In these two approaches, I have to describe what is the actual order. If the leftmost or the rightmost will lead to the same terminal, in this case, it doesn't matter. If I have an order, I have to use what we call it parentheses. Here, we want to consider what we call it derivation tree. And the derivation tree, it's a structure, or it's a graph or data structure where it exists inside compilers, and it helps us to drive through these symbols. So for example, I will deal with the S equal to A capital B capital, where A is either AA or capital A and or lambda, and B will be equal to B and small b and lambda or lambda. So in this case, S could be A or B. Then S could be A and A could be A or A, and B could be B and P, and this capital B and small b, and then A could be lambda, and in this case this will yield this particular AA, capital B and P, and then this B can lead to lambda, and then this B here can lead to B. So I will just break the derivation, and we call this derivation tree a parsing tree. Parsing tree is very common in compilers, and if you deal with programming language, you will learn a lot about it. Here we will do the leftmost and the rightmost, and if the order doesn't matter, both of them will give you the same tree. So if you end up having both the same tree, in this case you will be able to drive the symbol using the tree. Now there's always a question, what could I expect in an exam? It's very straightforward. If you have question, you say, given this particular grammar, show the driving tree. Drive this expression to the terminal A, B, and use the leftmost derivation or the rightmost derivation, and then validate the entries with a tree. In the next section, we will talk about ambiguity. And ambiguity will come when you have a mathematical expression where it can be interpreted in two different ways. So, for example, if I have grammar for the mathematical expression E, where E could be E plus E, or E multiple E, or the parenthesis of E, or the terminal A. In this case, I will have the expression of A plus A star A, the plus parenthesis A plus A star parenthesis A plus A parenthesis close parenthesis. So in this way, I will see this particular expression, and in this expression I will be able to drive it in the leftmost approach, where I will substitute leftmost, and I can validate this expression. So for the leftmost derivation for A plus A and A star, it will lead from this expression to this particular derivation. This is another leftmost derivation. You can see the derivation and the tree. If you do it leftmost first or rightmost first, you will see the two derivation tree will lead to the same answer. So if A equal to 2, at that case 2 plus 2, 2 star 2 will lead to the same answer. So in this example, you have 2 plus 2 star 2 will be equal to 6, and 2 plus 2 star 2 equal to 8. So if both the derivation will lead to different answers, in this way we have ambiguity. And to overcome ambiguity, we use the concept of parentheses. So if we have two different differentiation trees may cause problems in application, which we use derivation tree in evaluating expression. In general, in compiler languages, we will have some sort of parentheses or order to maintain or remove the ambiguity. Ambiguous grammar, it's a context-free grammar. G is ambiguous if there is a string W belong to LG or to the language of G, which has two different derivation trees or two leftmost derivation tree. So if I work out with this example and I expect to have a question, the question usually will be how or proof that this is an ambiguous grammar, or decide whether or not this is an example of ambiguous grammar. So if I look at this particular grammar here, This grammar is ambiguous since A star plus A star A will have two different trees. And by having two different differentiation trees, this grammar is ambiguous because if I do leftmost derivations, I will be able to receive two different ambiguous tree. If I go and say E equal to E star E or E star E, I can derive the same expression. This is here another example of ambiguous tree, or sorry, ambiguous grammar. So in an ambiguous grammar, here I'm using the variable as expression and sentences, and else is terminal. This is a very common expression. I can show here different sets of trees. So I do have two derivatives of the same tree, and the tree is not the same. So in general, ambiguous grammar or ambiguity is bad, and we want to minimize it or we want to remove it. However, sometimes it is possible to find a non-ambiguous grammar for a language, but in general we cannot do so. So a successful example here, this is an ambiguous grammar and equivalent. So in this ambiguous grammar, the E could lead to more than one expression. If the way to remove the ambiguity from this grammar is by transfer the similar symbols to they call it temporal symbols. So here, instead of saying E will lead to E plus E, then E will lead to another T, and T will be a temporal symbol. And I just need to make sure that at the end I will close the loop. So this particular set of different terminals or different variables will lead to a non-ambiguous grammar, because I cannot have more than one expression. So the things to watch for in ambiguous grammar is if you do an operation with more than two initial variables, if you do more than one operation between the same variables. These are the features of ambiguous grammar. If you studied state machine before, you will be able to make sense, because this will be basically temporal states. So if the machine will have some sort of ambiguity, to make it linear or to remove the ambiguity, you have to create more partial or more internal states. So if I have this grammar here where E will lead to E plus T or T, and T will lead to T star F or F, and then F will lead to parentheses E or A, and I want to make a derivation of A plus A star A, you will find out that using this particular grammar, the derivation is only one tree. This particular example, it's very common, because when we call about A to the power N, B to the power N, C to the power M union, A to the power N, B to the power M, C to the power M, where A and M, where N and M are not equal, and N and M are greater than 0, this has an inheritance ambiguity, because each one of these brackets will produce different subset. So here's how we show the example. So L will be either S or S2, S1 or S2, where S1 can be defined as S1 and C or A, and A can be A, capital A, B, and lambda, where the other bracket will lead to S2, where S2 will lead to A, S2, and B, and B will lead to B, capital C, or lambda. So if I want to build the trees for both, I will find that I may have two different trees for the same expression. So in this particular case, this string of terms, they do have more than two different derivation trees, and in this way it will not work as non-ambiguity grammar. If you have any questions, please email them to me. Please leave a comment below if you can. I'm looking forward to hear from you, and have a nice day.